this very special lecture, which is made possible by generous donation from Professor Starr's family. And also, I'd like to thank Dean Wenner and Dr. Joanna Chu and David and Maggie Scott for making this event possible. So today our speaker is Dr. Eric Betzig, 2014 Nobel Prize laureate in chemistry. So this is a great opportunity for our students, faculty to appreciate and celebrate his accomplishment. So Eric is currently a group leader at H.H. Mai's Gardenia Farm Research Campus, and it's even better to know that actually he's going to move to UC Berkeley this summer to be our neighbors. So Eric demonstrated perfectly what it means to be look beyond the boundary when explore scientific frontiers, and what it means to be one should follow one's passion. So he was trained as an experimental physicist, and he tackled the real-world problem in his father's machine shop. And he took an academic turn as a PI in Bell Lab and worked as scientific consultant. So what actually brought him back to academia? So the story started in 2002, and inspired by photoactivable protein, he built the very first prototype microscope that uses pulses of light to create image of a very high resolution than previously thought possible in a living room of his best friend, Harold Hess. So because of this pioneering and innovative work, Dr. Eric Betzig shared the 2012 Nobel Prize in Chemistry. He is the author of 29 patents and has published numerous high-impact papers. He has won numerous prizes for his significant contribution to science and impact he made, to make us to see smaller things in a cell. So he's now taking more exciting about imaging techniques, which I'm sure he will talk about in his lecture. So it may surprise you that Eric actually grew up wanting to be an astronaut. As a child growing up in 1960 and 70, that's true, Eric? Yeah. Right. Eric really inspired by the fact that watching TV as many as did, the human landed on the moon. So his love for space may not be his full-time career, but it's still part of his life. So instead of going into outer space, he dived into the inner space, invented the super high resolution microscopy technique to go beyond the diffraction limit to see the single molecule in action in single cells. So the title of his talk today is All Things Great and Small, the Roles of Telescope and the Microscope in Understanding Our Universe and Ourselves. I'm extremely honored to have Eric here as a star lecture speaker, so please join me to welcome Eric Betzig.
Very good friend of both me and my wife, Janelia. We were sorry to see her leave, but we're very happy to see that she's found a happy home here in Davis. I hope we can be just as happy at Berkeley in a few months. So if you want to hear more about what my lab is doing, you should turn in tomorrow. So this is the general lecture, and like Lynn said, I always have had the astronomy astronaut bug, and so a couple of years ago put together this talk about how the fields of astronomy and microscopy are related to one another historically. So that's what I'll give today, and tomorrow a little more detail on what our lab is up to. So one of the things, if you turn on Discovery Channel or National Geographic or these other science channel, is always about where are we in the scheme of things. So if we shrank ourselves down by a factor of 1 billion, we would be the size of the individual nucleotides inside of our DNA. But if we expanded our bodies by a factor of 1 billion, we'd only get to the orbit of the moon. And we would have to go another factor of 1 trillion to get to the size of the Milky Way. So we are really insignificant. You cannot fathom how insignificant we are. That we are 1 trillion times closer to scale to a molecule than we are to the galaxy. And that galaxy is only 1/10,000th of the size of the observable universe. Space is vast, and we are big on the scale of a molecule, but nothing compared to space. So how do we know this? How do we know all of that about the scale of the universe and the scale of molecules? Well, first you have to ask yourself, how much could we see in prehistory before we had instruments? And that's basically based on the physics of the eye. And so if you want to look at something up close and look at the small details of it, basically that's dictated by how far away it is you can put it from your eye, how close you can put it, the wavelength of light, and inversely with the diameter of your pupil, of your eye. Likewise, if you want to look off at infinity at stars or planets in the distance, you're just limited by the wavelength of light divided by the diameter of your pupil again, because these things are at effective infinity. And so both of these go inversely with the diameter of your pupil. So if you had bigger eyes, you would be able to see better on both the small scale and the big scale. But there's still limits for our size pupil. We can only see things about 50,000 times bigger than the molecules I was showing. And we can't even see Neptune as a disk. It's too coarse by a factor of 50. So how do we get to all the stuff I just said in the last slide? Basically, we create instruments that have bigger pupils to allow us to see smaller things. Those are called microscopes. And bigger pupils to see things distantly. Those are called telescopes. And so in modern microscopes, we hit up against fundamental limits, so we can see right down about half the wavelength of light. On the telescope side, there's no fundamental limit to how good our angular resolution is. And so we keep building bigger and bigger and bigger telescopes. So how did this play out over time? Well, in the prehistory of modern optics, first Archimedes, in probably an apocryphal story, was told to have used mirrors or lenses in the siege of Syracuse to burn the approaching ships with the light from the sun. In the 9th century, Abbas ibn Firnas in Spain was able to create colorless glass, and from these he made these hemispheres called reading stones with which people with bad eyesight by candlelight could then read things like the Bible. And by the 14th century, for the nobility or for rich people, eyeglasses were becoming common. But the real launch of sort of modern optics happened at the end of the 16th century, when the compound microscope and compound telescope were created. So Zacharias Janssen put together not one lens but two lenses and realized that he could see things sharper and clearer with better magnification with two lenses rather than one. A few years later, in probably another apocryphal story, Hans Lippershey was a spectacle maker, and in that story there were two kids who were playing with a couple of the lenses outside, and they managed to put two together, and they were able to see a weather vane in the distance, and that became the telescope, or the Dutch perspective glass. That took Europe by fire, and pretty soon everybody who was either in the military or nobility or whatever wanted to have a telescope even to see things locally, leastwise the stars. So the guy who really took this to a high level of refinement was Galileo Galilei, who made some of the best two-lens telescopes of that era. I mean, Galileo was the best at everything, but he was the best in astronomy as well. So with his telescope, he was able to look at Jupiter and find four little stars that rotated around Jupiter, which were then the Galilean satellites. He showed that Venus wasn't just a point, but a sphere that went through phases, just like the moon. He was able to show that the moon itself has craters and mountains, so it wasn't a perfect sphere. So all of these observations eventually got him into trouble because he was a great advocate of the heliocentric system where everything spins around the sun instead of the geocentric system. Got into fights with the Pope, had sort of a reconciliation, wrote a book to describe the Pope's point of view of geocentrism versus his heliocentrism, but basically made the Pope look like a fool in the book and then was put under house arrest and just spared the Inquisition for the rest of his life. So that's what a scientific career will buy you in the end. So microscopes were probably less quick to catch on than telescopes, and that's going to be a common theme that you're going to hear in this talk. But by the mid-17th century, things were starting to change. First, Robert Hooke, who was a tremendous polymath, also did just about everything under the sun like Galileo. He'd be far more famous today if he didn't have the misfortune to live at the same time as Isaac Newton. And these guys were bitter enemies, and Newton did everything he could to suppress everything that was ever known about Hooke, like burning his photographs or his portraits and things like that. But anyway, so Hooke basically made a compound microscope. He was the curator of the new Royal Society in London, so he did the experiments for them. And he was a fantastic artist and made pictures like this of this flea and wrote this book called Micrographia, which had all these plates with all of these pictures of things he saw under his microscope. And this took London by storm. It wasn't just the first scientific bestseller, it was one of the first bestsellers, period, and really made his reputation. And things like, first off, the perfection at which things in nature were at the scale of what he could see compared to, like, say, the point of a needle or something that man would make was really dramatic in terms of showing how different it was, how perfect nature was by comparison. And also things like the flea. This was at the time of the very last of the bubonic plagues to go through London, and so he was able to show these guys, again, are the carriers of these plagues, so at least you're able to put a scientific face on what's happening rather than just complete fear. Now, in a few years later, Antony van Leeuwenhoek came onto the scene. He was a draper who first used microscopes to look at the threads that would go into the drapes and decided he needed to make his own microscopes because he didn't like the quality that he had. And so he came up with an ingenious idea. Instead of grinding these lenses to shape, what he would do is he would take a rod of glass, heat it up, and then pull it like a piece of taffy, and it would have a long sort of like thread of glass. Then that would cool and he would break it, and he'd put that thread in the flame, and it would curl up into a little ball, and then he'd break off that ball, and that ball would be his microscope, that lens, and he would put it in a little thing like this that would only be a couple inches across with the ball up there, the sample on a little screw that you move up to the ball, and you look from the other side up against the sun and see what you want to see. With that, he made amazing discoveries, including eventually seeing single-celled animals, which were bacteria that he scraped from his tooth. He sent hundreds of reports, letters to the Royal Society, but when he told them he could see these things, nobody believed him, and they had to send a delegation over to Delft to look for themselves, and they saw sure enough that he was right. So he's known as the father of microbiology as a result of that. For all of his accomplishments, he's still not my favorite person because he was a secretive bastard. And he led everybody to believe that he was still grinding his lenses like everybody else, but kept this method of manufacture of the lenses secret. And as a result, he got down to 1 to 2 micron resolution, but it was going to be another 150 years before anybody else could make a microscope as good as his. So there was a lot of time lost by that secretiveness that he kept. So both microscopes and telescopes, as they got bigger and better with their lenses, started to run into a problem, which is that when you have a lens and you try to focus light, the different colors don't all focus to the same point. So that's called chromatic aberration. The first way to get out of this was Christian Huygens and others created what were known as aerial telescopes. So the amount that the rays differ at the focus for different colors depends on the focal length of the lens. And if the lens has a really, really long focal length, it's a very minor effect. And so they started to make two-lens telescopes where one lens was on the top of a flagpole, and then a long string would pull it taut to the other lens that they'd hold in their hand while they looked at this. So this is called an aerial telescope. So this sucker was 64 meters from there to there, and you have to like this while you're trying to see this thing. But with this, Huygens was able to see the rings of Saturn, show that they tilt as they go as different places around the orbit. And then Cassini, a couple years later with this, was able to see the division in the rings that bears his name. And his name is born again on that massively wonderful spacecraft that's still orbiting Saturn, at least for the next few months. So there's another way to get around this problem, though, which Newton discovered, because Newton, in his book on optics, understood from prisms how light is split by glass. And so he said, well, a mirror does not split the different colors. They all bounce the same way. And so he made a curved mirror to focus light, and therefore made the first reflecting telescopes this way, which basically allowed them in a much more compact instrument to be able to get good results. There was a problem. It's easy to polish a spherical surface on a mirror, but when you do that, again, you have a problem where all the light rays don't come to the same point correctly. That's called spherical aberration. So a guy who developed invented the octant also found a way to actually polish an elliptical shape to the mirror. And then the spherical problem was solved, and then all of a sudden they had a telescope that was just 1.5 meters long and then 15-centimeter mirror. And this outperformed this 64-meter behemoth that existed before that. So basically what you find in astronomy is a constant fight between the technologies of lenses and mirrors that went back and forth over centuries. In this era, the mirror was ascendant. So the best practitioner of that was William Herschel, who was actually a composer from Germany, who settled in England, and around age 35, he got bitten by the astronomy bug as just a hobbyist and started to build better and better reflecting telescopes, eventually culminating in the 40-foot telescope here. That would be him getting ready to look through the scope right there. So now all of a sudden we're getting to some pretty big scale here. He discovered amazing things. He discovered the planet Uranus, 4 moons around Saturn, 800 binary stars, and 2,400 fuzzy things he called nebulae. So he was the start of the catalog of all these astronomical objects. An incredibly devoted guy. The big problem in that era with making these mirrors is they were made of a mix of copper and tin called speculum, which tarnished really easily. So you would have to completely refigure the mirror every few weeks. And so he would spend 16 hours a day polishing these mirrors on one copy and then spend the other 8 hours of the day outside making observations at night. He was amazing in his work ethic, and all of it was due to his sister Carolyn, who worked as an astronomer at his side. So when he would polish these mirrors, he'd be going, you can't take your hand off the polishing compound in the rag as you're going around. So she would be feeding him lunch and dinner as he's going like this, because he was bitten by the bug, okay? So eventually an even bigger telescope in England was made called the Leviathan of Parsonstown. They were able to see the Whirlpool Galaxy with this. But both of these telescopes were really at the extreme limits of what people could, with the technology, get to work. And they were a pain in the ass, basically. And honestly, most of the real discoveries for Herschel was with his 20-foot telescope instead of his 40. And this one made minor contributions, but wasn't that big of a deal. But then we get up to the dawn of the 20th century, where finally we have really solid manufacturing technologies and so forth. And so then the Hooker telescope came on the scene at Mount Palomar, and this one was the telescope by which Edwin Hubble was able to look at these Cepheid variable stars. So these are stars that pulse in their brightness in a very periodic way, And people had found a few years earlier that there's a direct relationship between the brightness of the star and its period of pulsing, a linear relationship. And so therefore, you can, if there's a Cepheid variable somewhere, you can tell how far away it is based on how bright it appears and knowing its period. Well, he used that. At that time, there was a debate about whether the Milky Way was the entire universe or not. This is still the 20th century, understand. Early 20th century, people are debating this. Well, he started looking at Cepheids that were inside of the Andromeda Nebula, as it was called at that time. And then he did the math and realized that it was known the Milky Way was about 100,000 light years across. And the math told him that this Cepheid in Andromeda was 2 million light years away. So once again, all of a sudden, the universe, which in Galileo's time was first the Earth, then the solar system and the planets around Jupiter, and people didn't believe in heliocentrism because they thought the stars couldn't be so far away that there wouldn't be any parallax. But now all of a sudden we're out to 2 million light years. The shock that he must have felt in seeing exactly how the universe just expanded by orders of magnitude at that time when he saw that. And then, of course, right after the war, they finally finished the Hale telescope, which its 200-inch reflector. This was really the limits of what physics and materials can do to create a single mirror of a given size that's good enough to do optical observations. And this became the world's largest effective telescope for 50 years. So when I was in high school, I was such a nerd that I had every one of these pictures plastered on the walls of my room, okay, that I got from the Hayden Planetarium. But I was totally in thrall of astronomy and what could be seen with that type of telescope at that time. So during this whole process from the 17th century on, microscopy was still kind of stuck with these two lenses for a while. And then 50 years after, or well, first you have, I told you about this back and forth between lenses and mirrors for telescopes. So eventually, Newton actually wrote in his book on optics that it was impossible to create a multiple lens system that would correct chromatic aberration. It turned out that this was one of the few times where Newton was actually wrong. And so this attorney who in his hobby was doing telescopes figured that if he used two different glasses of dispersion of different kinds and cemented them together, he could create a way of balancing and canceling out those aberrations so all the colors meet at one point. And so he then went to two different glass makers to have the two different elements made because he didn't want anybody to catch on before he patented this idea. But those two guys subcontracted the manufacture of those lenses to the same third guy, and that guy kind of put two and two together and realized what it was all about, and then he patented it. Okay, and then or he didn't patent it, but he told other people about it, and then the first guy to actually use them in a telescope, this John Dolan, he said, "Hey, this actually works," and then he patented it, and then but he didn't enforce the patent because he knew it wasn't really his idea. But then when he died, his son certainly enforced the patent, and then it wasn't until that patent ran out that the price of achromats dropped by a factor of 2. So that took care of this, and then all of a sudden we were back in the realm. Because that speculum metal was tarnishing and a pain in the ass to work with, we then flipped back from mirrors to lenses because they solved the chromatic problem. And then eventually the lenses got so big that the gravity would actually distort the lens. And then at that time they figured out how to vacuum deposit aluminum on mirrors, and then mirrors took over again. But on the microscopy side, again, notice the difference in time, 1826, 1757. The sad fact is that microscopists are the retarded stepchildren of astronomers. And basically, we do everything 50 years after the astronomers already figured it out, and then we steal from them. This happens time and time again. And so it took that long before Lister, who was the father of the Lister, like Listerine, and who developed all sorts of antiseptic technology for surgery, he developed an achromatic microscope that would use this principle to get around chromatic aberration. They still had to deal with the same spherical aberration problem though. So a few years later, Lister and Ross figured out a way of changing the spacing of the lenses inside of the microscope to compensate for that, and then they were making, not consistently, but they could make good microscopes, but it was still very hit and miss. So with this type of microscope, they finally got back to where van Leeuwenhoek was 150 years earlier, and then we were off to the races. But the guys who really took microscopy to its ultimate limit was first Carl Zeiss, who was really educated as an apprentice in a machine shop, started a microscope company making single ball lenses like van Leeuwenhoek at first, but then eventually made a compound microscope, sold 1,000 of these. But he had a workshop full of people trying to put these lenses together, and there was just no rhyme or reason or any kind of science as to what would work and not. So he was the quality control guy, and he would go from workbench to workbench, and if he didn't like what he saw, he would take a hammer and he would beat the crap out of the microscope there and break it to pieces in front of the guy who was working. He was that frustrated and that motivated to make sure he made a good product. But obviously this is not the way to get rich, okay? So in his frustration, he finally made friends with a young physicist at the University of Vienna, Ernst Abbe, and he got Abbe interested in the problem of scientifically trying to figure out and calculate what kind of lenses would be necessary to create a good focus. So Abbe did that, found everything you need to create a perfect objective, also found that there was a fundamental limit that had nothing to do with anything about the materials, the glass or whatever, as to how small you could see, which is about half the wavelength of light. And that's known as Abbe's law. And that was fine, and eventually they got up to selling 10,000 instruments. But the only way they were able to do that is when they followed Abbe's prescription, they put these microscopes together very excitedly, they still worked like crap, okay? And what they realized was the problem was the glasses were not of uniform consistency of the lens, the glass in the lenses that the theory used. And so they needed better glass. So they hired a chemist in Jena called Otto Schott. And Schott developed new ways of mixing the stuff as the glass is annealing to be able to get pure glasses. And then finally they had this apochromatic objective which allowed them to get consistently to Abbe's limit, and the problem was solved. Now Schott was not stopping there. He basically created what was known as borosilicate glass after that, and that became used for the gas lamps in every country across the world and made him obscenely rich after that. Well, Abbe certainly got rich as well. Zeiss died, but that's the way the cookie crumbles. So since the time of 1880s or so, we've had really good microscopes, and as you know, it's become a workhorse of biological discovery. So, but that's not the end of the story, because even though those were hitting a theoretical limit, both microscopes and telescopes hit other limits other than just their physical size or their resolution limit as time went on. So this became really a big problem in the 80s and 90s, because in astronomy what people observed is that if you have a distant star, it emits light in plane waves that are traveling to the Earth, but the Earth has an atmosphere, and so those rays, those plane waves get bent like this spoon in this glass and water that looks like, and so it gets all distorted like this, and so coming into your telescope, they create a crappy image on your system. Basically, twinkle, twinkle, little star, right? So that's what a star looks like if you look at it up close in a good telescope. Well, that's garbage. The telescope should do a lot better than that, but because of aberrations, even the biggest telescope in the world won't have an angular resolution any bigger than an 8-inch reflector that a hobbyist might have in his backyard. It'll collect more light, but it won't do anything in terms of the resolution of what you can see. So that problem had to be fixed. It's the same problem if you had, like a day like today, if you didn't turn on your wipers, that's what you'll see, because The light is getting scrambled by the water on your windshield. Well, the same problem afflicts microscopy. So if you're looking at a very, very thin cultured cell on a cover slip, life is good and you can get to Abbe's limit of resolution. But here's a zebrafish embryo. If I look on the surface, I get a flat wavefront going in to give me a tight focus in my microscope, and on the surface, in this case a plant sample, you can see fine. But as you go deeper in, you lose resolution, you lose signal, and that's because the focus is becoming a fuzzy, ooky looking thing, because different rays are changed in their direction and the phase of their light because they're going through different material with different refractive indices going to the focus. And so this has become a big problem in both fields. There's two classes of ways in which both fields have solved this problem. The first is get rid of the aberrations. In astronomy, that means putting your telescope above the atmosphere, so space telescopes. So obviously everybody knows about the Hubble Space Telescope and what that's contributed. So this is what the Hale telescope, this is what I had on my bedroom wall of the Crab Nebula. And this is what you can see with the Hubble Space Telescope. Now this telescope has a mirror that's only a quarter the size of this mirror, okay, or half the size of this mirror, quarter in area. But still you can see the resolution here is much better because it's not afflicted by the aberrations that affect that one. So this is 10 times better than the best ground-based uncorrected telescopes. The only problem with this is it's damn expensive to put that up, and if there's a problem, the service call is even more expensive. So the problem is when they put that up there, they ground the mirror to the wrong shape. And so they had spherical aberration. They had to send the space shuttle back up to actually put in a corrective element to get rid of that aberration and then finally get to the beauty of what's been the Hubble ever since. And then with the Hubble, of course, thousands of beautiful experiments have been done. But this is, to me, one of the most awe-inspiring. So they've done this experiment a number of times over the years where they found a really, really empty, tiny little empty patch of sky where there wouldn't be any bright stars in the front. And they let the Hubble telescope stare at that spot for 11 straight days and integrate all the light that comes onto that camera over that period of time. So that black, empty piece of space looks like this. It ain't black and it ain't empty. So now you're looking 13 billion years into the past at the edges of the known universe. And what we can see now is that we're way beyond where Hubble was and way, way beyond where Galileo was. And now our universe is such that we're talking 100 billion galaxies with an average of 100 billion stars each, or 10 to the 22nd stars in the observable universe. Space is empty and space is vast, really vast. So how do you deal with this problem of the aberrations in biology? Because you have all of the things in tissues, the lipids, the DNA, the proteins, they all have different refractive indices that scramble things around. Well, one way that's become in vogue over the last 5 years or so is to put different chemicals in fixed tissue which basically extract out the various types of things that are of different index and replace them with things all of the same index. So you make what in one of the early papers was dubbed the glass brain, that you can homogenize it. You can still have fluorescent markers for things that you want to see, but then you can see it well. So this is one of those technologies which has some added features for super resolution that I'll go into detail tomorrow. But I look at this image, which this is like 250 microns by about 100 microns of mouse cortex. The volume is about 1/1,000,000th the volume of the cortex of the mouse. And you can see that this is only a very sparse subset of neurons, and the purple represents myelin sheaths that go around axons in the brain. And you can see how freaking complicated the brain is. I work at an institution where the goal is to do systems neuroscience to understand the functioning of brains. But I look at this and I despair at the complexity. It's just incredible how far we have to go. These are all dendrites and dendritic spines in the green and then the axons. But look at the numbers. In the human brain, there's 100 billion neurons, each expected to have about 10,000 synapses. So now you have 10 to the 15th synapses in one human brain. Well, there's about 7 billion humans on Earth, so there's 7 times 10 to the 22nd collective human synapses. Guess what that 10 to the 22nd was the number of stars in the known universe. So we as humanity collectively have as many synapses as there are stars in the universe. And, on a single brain, we have on the order of 10,000 times as many synapses in one brain as there are stars in our galaxy. So that's how complex the system is. So all of that's fine, but space telescopes are super expensive, and clearing the brain is not a viable option if you want to have a live brain afterwards that you want to study something about. So you have to come up with the second approach to dealing with the atmosphere or the refractive index inhomogeneity of tissue. So the way the astronomers did it first, actually the military did it first, but the astronomers picked up on it quickly, which is that what they do is they shoot a laser into the stratosphere to excite sodium atoms up there to create a bright artificial star that's next to the very dim object that they want to see. And then the light from both of those objects goes through the same atmosphere all the way back to the telescope with the same distortions to their wavefronts. You bounce it off a mirror, you pull out the bright signal you get from the artificial star, and put it in a sensor that can measure exactly how that light has been distorted. You then use a computer to change the shape of this first mirror in a way that exactly balances the distortions from the atmosphere, go back to flat wave fronts in a perfect focus. So this is showing that twinkle twinkle star again without what is known as adaptive optics, and then you turn the adaptive optics on and now you're back to the star you want. This is looking at Saturn through the Keck telescope that I showed in the beginning of my talk, or here there's Keck telescopes again, without adaptive optics and then turning on the adaptive optics. This is a cluster of stars near the center of our galaxy. There's a supermassive black hole there, and they can actually, with adaptive optics, watch the other stars rotate around that black hole at the center of the galaxy. And then just to show, this is, remember how wonderful the Hubble is out in space, but this is the view you get from the Hubble of Uranus with its ring. And this is what you get with that Keck telescope on the ground, but with the adaptive optics on now. So it's better than the Hubble in the infrared because the pupil's bigger. And we finally corrected for all the problems that the atmosphere provides. So again, my group and my wife's group and several others have decided to steal from the astronomers again and use those ideas of adaptive optics to be able to look deep into tissue, live tissue, with good resolution. And so whereas they shoot a laser up into the stratosphere, we use what's known as two-photon microscopy to excite just a single point inside of our specimen, in this case a zebrafish brain. And then everything else is exactly the same. You strip out that guide star light, you put it in a wavefront sensor, you change the shape of a deformable mirror in your microscope, and you can correct for those sample-induced aberrations. So here we're looking in the spinal cord of the zebrafish with a membrane marker. You can see the signal is reduced and the resolution is poor before the adaptive optics, but turn it on and it's great. This is looking at mitochondria in the soma of a neuron, about 150 microns deep. And again, everything is very fuzzy without, but with the adaptive optics, you can see the mitochondria as well as if that were a cell on a cover slip. What you've been seeing here as this movie goes by is a large fraction of the zebrafish brain where a subset of neurons have been labeled. The problem with adaptive optics in biology is you move your two-photon microscope from point to point, the light is focusing through different tissue, so you have to recorrect. So this represents 20,000 different adaptive optic corrections as we move around to get this image, but that all happens extremely quickly, much quicker than the actual imaging. So this is the midbrain region in the fish, and if we turn off the adaptive optics, that's what you would see with a normal, standard state-of-the-art 2-photon microscope, and this is what you see when you turn on the adaptive optics. So in other words, it's obviously quite essential to use this to get the best resolution possible. So, so then we get into the topic of, okay, we can correct and get resolution, but how can we get back to our theoretical limits of resolution based on the diameter of our mirror, or that lambda over 2 in the microscope that Abbe talked about. But damn it, we want more. You know, how can we see even more what's out there? Well, for planetary astronomy, the obvious answer is that while the angular resolution of something at infinity is only dependent on the diameter of the telescope, for spatial resolution, if you can actually move your telescope up next to the thing you want to look at, then at finite focal length, that comes into play as well. So the closer you get, the easier it is to see. So therefore, you go there and visit it. Okay, so obviously you can't do that for the stars, but you can do it in the solar system. And so, for example, with Mars, the first flyby was in 1965. This is from the Mars Reconnaissance Orbiter that's still going on around Mars right now. And this is showing the kind of resolution that you can get with that instrument going around Mars. This is now from Cassini, the spacecraft that's currently orbiting Saturn. And so this is one of my favorite pictures of all time, where you're basically looking, the sun is over here and Saturn is blocking the sun, so you're seeing just the scatter off of the rings. And that tiny, tiny little dot that you see there is the Earth. Okay. So again, gives you a sense of scale. And this thing went into orbit, I think, in 2005. And it's almost out of fuel and stuff, so they're going to deorbit it and into the atmosphere, I think, this September. But I'm going to mourn its loss, because the amount of data this thing has provided has been just amazing. So that's what we can do in astronomy for planetary science. So how can we defeat this theoretical fundamental limit that Abbe came up with to get higher resolution in a microscope? This is where I personally come on the scene, and it came in 2 stages. So when I entered graduate school, well, why would you want to do this? Well, the first problem is that if this is the size of a protein molecule, then this resolution limit of Abbe says that protein molecule looks like this big fuzzy thing in a microscope. Well, obviously that's a problem, because if you want to understand at the most fundamental level how inanimate molecules self-assemble to create the animate cell, your tool to look at this live is too coarse by a factor of 100. You can look at an electron microscope and so forth, but you're not going to get the dynamics to really be able to tease out the story. You want a live imaging tool that can see to the molecular level. So when I was in grad school, the method we developed was something called near-field scanning optical microscopy, where we would take a pipette such as used in electrophysiology experiments, pull it to a taper, which would have a little hole on the end. Then we would coat the sides with metal, leaving a hole that's about 1/10 of the wavelength of light big, and put that very close to the sample, so it acts like a little nano flashlight that just illuminates a little region, drive that around, and get your image. So with that, at one time we had the world record for data storage density, where these were optical bits recorded by diffraction limited techniques, and this is what we would get in our microscope. And here is what you would see on a normal cell with a regular microscope, and this is what we would see with the near field microscope. So I invested about 12 years into my life with this technology, and for biology it was a complete dead end, because the problem is that even if you move, say, 25 nanometers away from the sample, which is about only 1/10 of the thickness of the very thinnest parts of the cell, then you completely lose resolution. So only the very surface of any cell would be accessible, and driving this thing around point by point was both destructive and slow. So it was really, for biology, a dead end. Now let's turn back to how astronomers have dealt with this problem of limited resolution, particularly in the context for, you've been hearing a lot in the media over the last 10 years about the discovery of planets around other stars. Well, how do they do this? Because it's only a very rare few stars which are close to us, that have massive planets that are way out from the primary star, so you're not blinded by the glare of the primary star, where you have enough resolution to directly image it. That's not how they find exoplanets in general. So they have to find other means to do this. There's several different ways. So one of the first really successful ways was as the planet orbits its star, it pulls on the star just as the star pulls on the planet. So some of the time it's pulling the star towards the Earth and sometime away from the Earth, which because of the Doppler effect slightly shifts the color of the light from that star. And so they can measure that in order to find out that there's an exoplanet orbiting. But what has turned out to be by far the most prolific way of finding exoplanets was by the transit method, particularly with the Kepler telescope that was put into orbit. So this is an unwinking sensor which looks at hundreds of thousands of stars in space and just measures the intensity of the light recorded from those stars. And if a planet ends up eclipsing the star, then there's a very small dip in the brightness of that star, which is a signature of the planet. How quickly it dips tells you the diameter of the planet, and how much it dips tells you the size of the star. So all of that is obviously a big area. So how do you tease more information than the limits of physics out of your system by using tricks like that? Well, this then brought me back ultimately to trying to deal with super resolution again about 10 years ago. And so the thought that occurred to me and my buddy Harold was that if that single molecule looks like a big blob that you see there, the problem isn't so much finding where the center of this blob is. I think you can all see the center of the blob is there, right? So you kind of know where the molecule is if there's just one molecule. The problem is that in a biological sample there will be zillions of molecules all bumped up against one another and all these fuzzy blobs overlap and you can't find a center in there worth anything, right? So how do you deal with that? Well, my buddy Harold and I on a trip to Florida State in 2005 learned about a new kind of fluorescent molecule, a fluorescent protein, which normally with a fluorescent protein, if you shine blue light on it, it'll glow green. But with these photoactivated fluorescent proteins, you shine blue light on it, nothing happens. But if you first shine violet light on it, you activate it so then it becomes fluorescent, and then when you shine blue light on it, it will glow green. So this is after shining the violet light on and then shining the blue on. And so we realized that if you turn down that violet light really, really low in intensity, then statistically it's likely that only a couple molecules will turn on at any one time, and then they will likely be separated by more than the size of the fuzzy blob. And if that's the case, then you can find the centers of those isolated molecules, turn off those molecules, turn on another subset of molecules, again and again and again, thousands of times, until you find the location of every molecule in your sample. So this was an idea that excited us a lot, but it also terrified us because we were like, why hasn't anybody done this already? This is so ridiculously simple. And so we were terrified of being scooped. The bad news is at that time we were both unemployed. But the good news is that, I did that near-field microscope at Bell Labs, and when I left in '94, I was so frustrated I just told them to all go to hell. But Harold is much smarter than I am, so when he left in '96, he was able to take all of his equipment with him. So he was able to pull that out of the storage shed, and then we put in about $25K each of our own money, and we put it together in the living room instead of the garage because he wasn't married, so there wasn't anybody to complain if we didn't. And then the bad news is we knew nothing about biology at all, and so I was scheduled to give a talk at NIH, and I asked when I was there to meet the inventors of this photoactivated fluorescent protein. And that was Jennifer Lippincott-Schwartz and George Patterson, and I told them our plan, and they said, great, bring it by. And then within a few months, we were going from, this is a cut through lysosomes in a cell, diffraction limited to the palm image, and to better appreciate palm for photoactivated localization microscopy, the improvement in resolution. And that's what got me to Stockholm then in 2014. But certainly not the way you would have planned it. Don't ever plan to try to get a Nobel Prize. It doesn't work. So anyway, so modern applications of this technology. Now we can look at much thicker samples with much higher molecular densities to see in much greater detail at higher resolution. So this is a cell in telophase here. Here are the retraction fibers. There's the endoplasmic reticulum inside and so forth. Now it takes a super long time to, as you can imagine, to get a palm image because you're turning on sequentially one small subset of molecules after another. But there's sort of a halfway house to do live imaging, and one of the best examples of this is by my colleague James Liu at Janelia, where he was interested in studying the Huntington protein in Huntington's disease. So these are the nuclei of 2 live cells. This has the wild type protein, and the Huntington protein you can see forms these tiny little aggregates, but they don't stick around and they're small. But when you have the glutamine repeat that leads to the disease, you get these large aggregates in the nucleus. And then James was able to show by, again, sort of turning on subsets of molecules palm-like and watching them diffuse, that these aggregates actually act as sort of quicksand for transcription factors that are necessary for gene expression. So basically you end up down-regulating gene expression because of the existence of these aggregates inside of the cell. So kind of relating a disease to events happening at the single molecule level. So all of that's fine, and we've seen all of these analogies between astronomy and microscopy, but there's one point where it breaks down, which is that except for a few things like the volcanoes on Io or other things, on human timescales, the universe is a very static place. But biology is anything but static. In fact, the thing that defines life is that it's animate. And so, to me, every living thing is a thermodynamic pocket of reduced entropy through which matter and energy is flowing continuously. So while high-resolution structural images like we get from electron microscopy or palm are always going to be important, in my opinion, the only way we're really going to understand life is by studying it with high resolution across all 4 dimensions of space and time at the same time. And so that quest, starting in 2008, which happened when I was very frustrated with palm, just as I was frustrated with near-field microscopy 13 years before that, eventually led to what we call the lattice light sheet microscope, which is a technology to create a very thin sheet of light that we move quickly through a live cell to get images. And here's an example where you're looking at a primary T cell attaching to a dendritic cell to create what's known as the immunological synapse to find out exactly what is the infection that is being carried in information, MHC complexes on that dendritic cell. Here you're looking at a pond protozoan called Tetrahymena that's trapped in a little pocket of agarose and wiggling his way around. 3 volumes a second for thousands of volumes without harming the cell. Here you're looking at Drosophila fruit fly embryo, which is folding up epithelial cells around it as it develops. Here you're looking at 3 different proteins in a dividing cell, looking at the mitochondria in yellow, the endoplasmic reticulum in pink, and histones that mark the chromosomes in the nucleus there. And here you're looking at a little worm embryo which is going through its initial divisions. So to me, this is my Galileo moment. I mean, I don't like to pat myself on the back too much, but I'm very proud of what Palm has done. It's nice to win the Nobel Prize for it, but I have never felt more like Galileo than with this microscope, because every time a new group comes to our lab, we see something new. It's like Galileo pointing his telescope at Venus or Jupiter or whatever, and you see the cell in a new way. So the last problem that we have to face with that, though, is we want to apply that high-speed 4D imaging tool not on cells on a cover slip anymore, because cells didn't evolve there. We need to study cells in their native environment, in the parent organism, and for that we need the adaptive optics I talked about before. So our latest microscope combines the lattice light sheet with the adaptive optics. So in this case what you're looking at is a space in the developing ear of a zebrafish. These are skin cells This is the hindbrain with somas there. And what you're seeing here, this little guy, that's a neutrophil, a white blood cell that's basically the garbage scavenger of the cell. And with the adaptive optics on, you can see what amazing contortionists that these guys are and their ability to fit in between these little cells in between and all this. And the blue is basically dextran particles that represent the garbage for this guy to sweep up. So for me, studying a cell and studying cell motility on a cover slip or studying cell motility in a collagen matrix is like watching a lion in a zoo. But this is like watching what a lion does on the savannah. Okay, so to me, this is really the future of cell biology because we know that the dynamic and structural phenotypes that we observe in our microscopes are the end result of gene expression, which in turn are influenced by local environmental cues. So if you don't get the environment right, you're not going to get the physiology right. And so where do we go in the future? Well, with astronomy, there's big plans for both. You know, again, some of the biggest telescopes now are 10 to 15 meters. There's plans for the 30-meter telescope, which was going to be in Hawaii, but there's a lot of local resistance to putting it on the mountain there, so it may end up in the Canary Islands. Europe has an even bigger telescope plan, the extremely large telescope. The Hubble telescope will be replaced in 2018, we hope, by the James Webb Space Telescope, which will go out past the moon in very dark space, where it can look in the infrared and basically have a much bigger mirror with adaptive optics on it as well, to be able to see way beyond anything we've seen before. And now with adaptive optics, they're being able to do next generation type of adaptive optics to be able to look at very large fields of space with correction. And so just to conclude, what amazes me is exactly how far science has taken us in our understanding of the universe around us, the big end and the small end, in just 400 years. 400 years ago, Galileo was defending his stuff before the Pope. And we knew so little then. We still know very little, but we know a lot more than we did then. And it's really amazing that we've been able to go this far. And a lot of it has been by people working alone and people who aren't, you know, who are either self-funded or have second jobs and doing it as a hobby or whatever. And it really shows the passion that goes into scientific discovery. You know, that it isn't about necessarily big groups and big efforts and big governments all the time. You know, that there really is this human element that's involved in science progressing forward. And it's been a real privilege and an honor to be part of that process. Thank you very much. Turn up the lights if you'd like. Somebody. There we go. At least up here. Yeah. Okay.
It's a maiden lecture, and Eric would like to take some questions.
Anybody? Don't need to be shy.
Yeah. Okay.
There's we got somebody to break the ice. Okay.
Thank you for the illuminating lecture on your journey to discovery of this, your Nobel work. Now, I want to pick on your word, that you did not like a particular scientist because he has hidden the...
Yes. Yes, Van Leeuwenhoek.
So
yeah.
long.
Yes.
Well, my whole challenge to you is how many people have you mentored?
Yeah.
In this journey of discovery.
Right.
And how many continents have you covered?
How many what?
How many continents?
Oh, all of
have
them.
you covered
All of them.
in this journey?
Yeah.
I mean, if you say you have mentored people, have you mentored people from all the continents?
Not yet. I'm
Not
too small a
yet.
lab, yes.
Well, will you be willing to mentor anybody from Nigeria?
Well, if
the biggest
if they can,
country in Africa.
if they're the right person for my lab, I would absolutely take them on. Okay.
Well,
But let me argue more broadly than that. Okay. The number of people I can put in my lab is a very restricted number, right? I mean, there's 7 billion people on Earth.
Okay.
I can take 4 or 5 at a time. Okay. So let me tell you how I try to address that problem. Okay. A very big part of our effort in our group is to be the anti-Van Leeuwenhoeks and make sure that our technologies are disseminated. So we do that in various ways. The first is that a lot of people aren't about wanting to build the microscope, they're about wanting to use the microscope. So what we've done is we've created an imaging center at Genelia that have copies of these microscopes where people can come at our expense to come and apply these microscopes to problems. But even that's too narrow of a bottleneck. So the second stage is that for all of our microscopes, we document down to the screws and every line of code for how to build your own. We put on workshops where people from Nigeria would be glad to come, happy to come, and then you can learn how to build one for yourself. We videotape all of those workshops. All of that stuff is online. So we tear apart a microscope and we put it all back together again, and every part of that process is documented. There's at least 100 different groups building that lattice light sheet right now on the basis of that stuff. And the final step is, like it or not, and I don't care about the money, but you have to commercialize these microscopes for them to have a broad impact. Because having worked in industry myself, I understand exactly how laborious the product development cycle is to make something that's turnkey so that people can use it, right? And that's what companies contribute to the thing, but the companies won't be willing to invest the time and effort to do that unless they think there's a market. So there's kind of a chicken and egg problem. So a lot of our imaging center is to basically prime the pump and get a lot of initial applications out to create a demand for a commercial instrument. So we really work very hard to be the anti-Van Leeuwenhoek, and I think it goes a lot beyond just how many people are directly mentored by me, which can only always be a very small number, but actually expand beyond that.
Okay. Thank you very much. Thank you.
Anything else?
Anybody have any questions?
No?
Wow.
Okay, good.
So perhaps just in general, not that much about science, but I was reading about your biography today and
Yeah.
in relation to this, and it's kind of inspiring that you basically been doing a lot of this stuff. But one of the things that kind of shocked me as a young scientist myself is that you mentioned you haven't had to write an R1 or a grant.
I've never written a grant in my life.
So
Ever.
I'm wondering, how are you going to approach that in your new
At
position
Berkeley.
Berkeley?
Well, that's a good question. I kind of wonder that too. Well, I'm going to take a three-prong approach to that. So the first is that I happen to work for the greatest institution in biology, the Howard Hughes Medical Institute. And although I won't be at Genelia, I will still be an HHMI investigator. So that's a pretty good pot of money to draw from for a while, okay? Second, I held Berkeley's feet to the fire on my startup package. So that will insulate me for some period of time. But the third thing is the lesson I've learned in my life is that I've worked for 2 philanthropies so far. I considered Bell in its heyday a philanthropy, okay? HHMI is certainly a philanthropy. You've seen, even in this century, how many times rich guys are funding things they care about, right? Now the latest is the Chan Zuckerberg, Institute and the BioHub, but there's, Allen Institute, on and on and on. And you can see from this talk that historically government funding of science is a very recent invention. It's really something that's a post, the Vannevar Bush endless frontier thing that's kind of this post-World War II thing that came out of what science was able to contribute in World War II to the winning of World War II. But historically, it's been either self-funded people or people funded by rich dudes who have been able to do science. So I would not want to put up with the hassle of an R01. And I would rather knock on the door of rich people and say, hey, I'm doing something cool, would you please give me some money to do it? Okay, so it helps to have the shiny metal too to get them to open the door, but yeah, yeah.
So I will always inspired by Eric's passion, that he really demonstrated what it means to be, one should follow one's passion. It's all about, once you're passionate about science, that's a reward about.
Yeah, absolutely.
Yeah.
So. Win or lose, fail or succeed, at least have fun doing it, right?
Yeah. And believe yourself.
Yeah.
Maybe this is a little bit technical, and I don't know whether you're going to explain it tomorrow. I wonder, is there a limit on the time resolution in your, if you want to see the line, jump in the
sure.
bars.
Yeah, there's always limits. In fact, one of the things you're going to see tomorrow is I put up a tetrahedron, like a pyramid, okay? And I say every microscope involves trade-offs. And if you want higher spatial resolution, it's going to cost you speed and phototoxicity and imaging depth and vice versa. So as you move to one vertex, you move away from the others. You can try to be as clever as you can, but you still run into those limits. On the speed limits, frankly, right now, we're limited by camera technology. Okay, so we use these SCMOS cameras that have come on the scene in the last 6 years or so for the lattice light sheet. And, I have to say throughout my entire career, you could document every advance in technology I've made is just a piggybacking on some improvement in detector technology. So EMCCDs made Palm easy. It's because you had single molecule sensitivity. And the SCMOS has made lattice light sheet easy. And I was the first guy to see single molecules at room temperature with my near-field microscope, which was made possible by the single photon counting avalanche photodiode that had just come on the scene at that time. So, one of the very greatest things about, so from 95 to 2004, I was out of science altogether, and I never read a paper or did anything. And when Harold and I came up with the idea for Palm, and we were starting to put our plan together, it was amazing to see how much, commercial technology had advanced. I felt like Rip Van Winkle, in terms of, dial pump solid state lasers and EMCCD cameras and dichroic filters or other filters from Semrock that were way beyond any technology we had before. And all this stuff that was either at the very edge of doability or impossible to do 10 years earlier was now almost trivial to do, so yeah.
Thank you for your presentation. When you use adaptive optics combined with the lattice light sheets, how do you deal with motion artifacts?
Yeah, so basically we move generally much faster than the sample itself does. So the one exception to that is actual single molecules in 3D, where we're generally not fast enough to track in 3D. But if it's typically, vesicle size, like endosomes or something like that, we're fast enough just even sweeping our light sheet that we can follow that along. Now, on the adaptive optics side, the thing that helps is that the refractive index variability of biological tissue, even in a developing organism, doesn't change rapidly, okay? So that what we do when we're looking over a large embryo, and remember I said we have to have different adaptive optic corrections in different parts of the tissue. But once we go back to do the next time point of imaging, we only need to investigate some subset because you don't need every time point to completely redo the adaptive optics for everything. You can kind of scroll it and do with some subset and do it that way. That's very different from astronomy, where the aberration is completely different on the millisecond scale. So those guys have to go boom, 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 and get new aberration corrections, but they only need one, whereas we need a bunch. So there's differences and similarities between how adaptive optics is applied in the two fields. Yeah.
Any other questions?
Okay.
I think we have actually a big group of students,
Okay.
undergrad and graduate students. They could be the next generation scientists. I'm just wondering if you can give some advice to our students.
Yeah, I can give a lot of opinions. The first one you've already said is whether you do science or whether you do something else, do the thing that you feel passionate about. My feeling is that a career in science is never going to be harder than it is going to be for you people, because frankly, you know, the enterprise is broken. I feel like every professor has created the problem by having too large a group, which has created too many of their progeny who want to be professors as well. This is why R01 rates are down to 12%. And so you've got a nonlinear system where people are writing grants, reviewing grants, and nobody's getting any grants. And that doesn't exactly advance science in a meaningful way. So if you're going to be a scientist and want to have your own group to do science, you damn well better do it because you love it. I mean, really love it, and you can't imagine doing anything else. There's a lot of people in the younger age who do it first because they're good at it. They're better in high school than their peers at science, or they feel the peer pressure of their family or something else to continue to do it. But if you don't internally do it because you really love it, find something else you love, because it is a hard life, and it's going to be never harder than it's going to be for the next generation. I hate to end on that down note, but I'd be happy to talk about it more at length. Okay.